Okay guys, in this video I like to show explicitly how to get to this expression, which is the total differential for a thermodynamic function that we call enthalpy, right? So in class we discussed this equation and we did something with minor derivations here and there, but a sticking point that we had in class was, how do we get this? What is this term? Okay, so that's the point of this video, to show how we arrive at this component of the entire equation. So let's start first by remembering the functional dependence of H, enthalpy, and two properties, temperature and pressure. Okay, so enthalpy to be considered a function of temperature and pressure. And because of that, we should be able to write down the general form of the total differential of this function as dH dt constant P dt plus dH dP H dP constant T dP. Okay, so that's the general form. We should be able to do this, right? We also should be able to recognize this term here, right? Changes in enthalpy with respect to changes in temperature at constant pressure. Well, that's nothing more than heat capacity at constant pressure. So dH is equal to this term being recognized as Cp dt. Therefore, what we are after here is to show that this component, right, is equal to dH dP at constant temperature. That's the goal, right? Okay, so now we have identified the problem. The problem is this term. How do we go and reconcile these two terms? Like this is equal to this. Okay, so we're going to do that in the next few minutes. Okay, so let's start with the fundamental definition of H. H is defined as internal energy plus PV. Again, this is coming from what we learned in class. H equal or defined as U internal energy plus PV. So that means dH should be equal to du plus PdV plus VdP, right? Or basically equal to du plus dPV. So this dPV has been expanded as PdV plus VdP. That's all I have done so far. Okay. dH. What have we learned about dH? Well, we learned that dH is dH is equal to Cp dt plus dH dP constant temperature dP, right? So that is dH, and that's equal to du. What have we learned about du in past videos and in past lectures? Well, du is equal to Cv dt plus du dV, right? Temperature times dV. And why is that? Well, guys, remember, H is a function of temperature and pressure. Let me write it down here. H, function of temperature and pressure, and U is a function of temperature and volume, right? That's U. So that means du should be du dt, right? U dt times dt, and the u dt is just Cv. And then the u dv times dv. So we have, that's the reason we have these two terms here, because of the du. Okay, so that's kind of recalling our previous knowledge. Then I keep going. So I'm done with this term. I move to this one, plus P dV plus V dP. Great. Things to consider now. We are interested in this term here, right, which is nothing more than the HDP constant temperature. So we are now going to consider that constraint, that this is constant temperature. So at constant T, so that we can arrive at this expression here, we can argue that this term goes to 0 because it's constant T. This term goes to 0 because it's constant T. So all you will have is the HDP constant T dP equal. CVDT is gone because it's constant temperature. Equal du dV. So there is a common factor dV and dV here, common factor. So I will consider that as du dV, constant temperature, plus P dV. So these two terms have been combined into this term, plus V dP. Great. Okay. So if we keep going, let me use a different color now to highlight the important results here. Well, du dV. In previous videos and in class, we learned that that's equal to what? Think about it. It's equal to what? Du dB. In the meantime, we'll write this down. Well, du dV, hopefully you remember, is T dP dt, constant volume, minus P, right? And then plus P, because we have this P here, so plus P dV plus V dP. Okay, we're in there. So what's striking about this? Well, one thing that's striking is that this P will cancel with this P. So that's no longer going to be there. Also, that we are close to getting to the HDP equal to something. So we just need to solve for it by moving the dP to the other side of the equation. So let me do that. Okay. Remember, this is the goal, the HDP constant temperature. The HDP constant temperature. So just move dP to the other side. So we'll do that in the next few minutes. Great. So what do we have? We have the HDP constant temperature equal, so this P goes with this P, cancel, so we have T dP dt, constant volume. Oh, we have the dP here, so keep it. So we have the dV plus V dP. So what do you guys think is natural to do now? Right? What will be the next step? Well, divide the whole equation by dP so that we can have this on its own, by itself. So that's what we're going to do next. Okay? So let's divide the two sides of the equation by dP. So if we do that, then we end up with this, the HDP constant temperature equal T dP dt constant volume, and then dV dt dP constant temperature, right, plus just V, because dP divided by dP will give you just 1. Okay? So we're there. Very close, right? So we had the V already, the V, but we have the T here, but instead of having two derivatives here, we only have one. Partial derivatives, we only have one. So, and then there is a negative sign that we don't have here. So any suggestions, right? So there seems to be 1, 2, 3 derivatives related to one another. And that relationship seems to be related to the negative sign, right? Well, you guys remember, this is nothing more than the cyclic rule again, right? So, cyclic rule. In fact, let me actually recall that cyclic rule on this side so that we can continue later here. Cyclic rule. Okay? So we have dP dt constant V times dt dV constant P times dV dP constant T equal to, probably know that by now, equal to -1, right? So you think about it, we have dP dt, dP dt. We had dV dP, dV dP. So basically we have these two terms. So then dP dt constant volume, dV dP constant temperature has to be equal to minus the reciprocal of this derivative. So minus dV dt constant P, right? So you see now the negative sign seems to make sense. And we had the dV dt term that we were looking for. So, okay. Using the cyclic rule, then we can see that this is equal to minus T. These two is equal to minus dV dt. So minus dV dt constant pressure plus V. And this, my friends, is the term that we needed so that we could account for this portion of the total differential of the enthalpy. So that's the goal that we have, and then I think we have accomplished that goal. So make sure you guys review it as many times as needed and try to have fun as you do that, okay? Thank you very much.